Hello, welcome back to my channel, and in this video we're gonna keep discussing about the normalization of the wave function. This is the part 2. Okay, so in the last couple of videos we have learned about the wave function, and when you square the wave function you get this probability density function. If it's a probability density function, it need to follow some of the probability axioms, and one of them is normalization. And what it means that when you integrate from minus infinity to plus infinity of your probability density function, that must be equal to 1. But we have learned that the wave function collapses and it evolved differently than it was before. So the question is if the evolved wave function is normalized or not. If it's not normalized, it become very tedious because you have to normalize your wave function over and over again, and you don't want to do it. We want to check it if the normalization condition changes with time. And the answer is it does not change with time, which make your life easier. But in this video, I'm gonna give you proof of that it doesn't change with time. So basically, if you want to check something that doesn't change with time, you take the derivative of that thing with respect to t. If that thing changes with time, you're gonna get some non-zero answer. If that thing is constant, you're gonna get answer as 0, and that's what we're gonna check. So this is more mathematical than usual. So now you take the derivative with respect to t, and you have this normalization condition. So these are some mathematical trick. You have this d over d of x, you're going to take that inside. Now this become partial derivative because you have this 2x and t. Full derivative become partial derivative when you differentiate function with two variables and you just differentiate with respect to one. Okay, so you have this. Now we want to differentiate this thing with respect to time, and when you open this square is basically conjugate of wave function multiply with the wave function, and you're gonna apply the basic chain rule where you multiply with the first, differentiate the second, and differentiate the second, multiply by the first, and you get this expression you have here. And now what you're gonna do is what you need is you need to know what this psi d psi over dt is and d psi conjugate over dt is, and this is you get from wave equation. Wave equation gives you these two derivatives. You can go and check that by yourself. I just rearranged the wave, our Schrödinger equation. We get it from Schrödinger equation, not the wave equation, which is the wave equation. But I just manipulated the Schrödinger equation a little bit, and you can go and check by yourself that you get these derivative from the Schrödinger equation. And the next thing is you're gonna substitute back these two derivative into this chain rule equation. And what you're going to get is this simplified expression, and this is your homework to check. Go put this thing and substitute that, and you will get this answer. And now one trick you can do here, you can take one of the derivative outside because you have second derivative, and you can check this one also. When you do the mathematical manipulation, you can get this second one of the derivative out. But how does that help? Now if I have this derivative, which is partial derivative of with respect to x, I know my differentiation is with respect to x. So when I plug this thing into this integral, you're gonna get the answer, this answer as your integration answer. This is basic integration that you learn in calculus class. The important is you're gonna get this as your answer of your integration. And yeah, you have this answer from the integration where you have now you're plugging this upper limit as plus infinity and lower limit as negative infinity. So one of the condition your wave function should follow if the wave function is normalized is that when x goes to infinity, plus or minus, your wave function should go to 0. Otherwise, your wave function would not be normalized. And this is the condition all the normalized wave function should follow. If your wave function is not following this condition, then your wave function might not be normalized, and that would not represent physical situation. So all the normalized wave functions must have this where when x goes to minus infinity to plus infinity, your wave function should go to 0. And when you plug your limit, this whole expression goes to 0. And equation, you now check that when you differentiate your normalized condition with respect to t, as the time evolves, it does not change with time, and this tells you your wave function stay normalized. So this was the proof. If you have any question, please let me know. I know this was the more mathematical than usual, but I can simplify some of the question if you have. Let me know in the comment, and I hope you like this video. If you do, give it a thumbs up, and I will see you next time.